Hi everyone, this is the second video of this weekly digest. In this video, we are going to walk through the measure of centeredness, the measure of spread, the empirical rule, and a lot more. The measure of centeredness involves three concepts: the mean, median, and the mode. You are supposed to know how to calculate each one of them. In order to get the mean, you add everything up in the sample and divide them by the sample size. It is pretty simple and straightforward. The median involves sorting the data in an ascending order or descending order. It's up to you, and find the observation in the middle. Of course, if there are more than one observation in the middle, you simply find the average. And in order to get the mode, what you want to do is to find the value that shows up the most frequently. On the other note, the measure of spreadness involves the standard deviation, the variance, and the range. I think the difference between the range and standard deviation is pretty remarkable, because in order to get the range, you only have to take advantage of two values, the maximum and the minimum. And in order to get standard deviation, you have to use every piece of information in your data set. And another difference is the range is quite sensitive to the outlying distribution. Just think of a scenario in which you have a very large value as an outlier in your data set. Because you have to utilize the maximum, probably your range will be different if you are including that outlying observation. However, standard deviation is much more stable compared to range. Empirical rule gives us a quick and dirty way to have a bigger picture of what's going on in the population. For instance, if you know the standard deviation of population is 1 and you know the mean is 0, then you can say 95% of the data will be living in between -2 to 2. Of course, we have to be clear about certain assumptions of this distribution, like this distribution has to be bell-shaped and symmetric. Before we move on and talk about stuff in Chapter 3, I want to quickly discuss the difference between the inferential statistics and descriptive statistics. The major difference between them traces back to the argument of population and sample. By definition, population is a collection or set of every individual you want to investigate. However, because of the limitation of time, money, resource, you cannot investigate every one of them, so you have to take a small portion to represent what's going on in the population, and that is called a sample. So in a sample, usually we can pull out some valuable information like mean, median, standard deviation, stuff like that to represent what's going on in the population. So if you are going that route, by which I mean if you are using the information from the sample and try to make a guess about what's going on in the population, then you are doing inferential statistics. And in contrast, if you are pretty satisfied with what's going on in the sample and don't want to look into the population, then you are doing descriptive statistics. By definition, sample space is a collection or a set of all the possible outcomes. And any subset of them is called an event. It's that simple. So to help you understand, just try to think of tossing a dice. And that is a random experiment. It has 6 possible outcomes from 1 to 6, and that makes it a sample space. And any subcollection of that is an event, like the event of seeing a 6, or the event of seeing odd numbers, the event of seeing even numbers. Okay, in terms of the probabilities, we talk about some axioms. First and foremost, the probability of any event is between 0 and 1. So in any of your exam questions or homework questions, if your calculation of probability gives you maybe -1 or 1.5, you should know that there is something wrong seriously. And the second thing you should remember is, in order to calculate the probability of something not happening, you can use 1, subtract the probability that this event is happening. Moving on, we also talked about the operation of sets. This is because the events, they are essentially sets. So in order to understand the operation of events, you have to understand the operation of sets. And there are 3 major types of operations, just like add and subtract. We have complement, union, and intersection. So union means it has to be in either A or B. And intersection means it has to be in both A and B. And complement means not in A. So that's the 3 types of operation you have to bear in mind. And there are some special cases. For instance, if you have A intersect B and you got nothing in common, there is no overlapping part between A and B, then we define A and B as mutually exclusive, or in other words, we call them disjoint events. And based on all that, we introduced the addition rule, and that is given as follows. The probability of A union B equals to the probability of A plus probability of B minus the probability of A intersect B. You have to subtract the common part, otherwise you will be counting them twice. Of course, if your events are disjoint, you don't have to worry about that part because there is no overlapping part whatsoever. Conditional probability is a very important concept in statistics, and it is also very intuitive because our notion about the likelihood of a certain event is going to be changing as we learn more information. So for instance, just consider the past 2016 election. We can roughly say that 50% of American voters voted for Trump. So that means a random person that you pick on the street have a 0.5 probability voting for Trump. However, if I give you more information about this particular voter, let's say she has a graduate degree and she is a minority, then probably that likelihood is going to change by a lot. So that is conditional probability. In this class, you should be able to first understand the concept of conditional probability. You should be able to know how to calculate a conditional probability based on a tree diagram or a contingency table. You should be able to know the difference between A and B and A given B. This sounds a little weird, but it's really quite confusing when you're looking at a tree diagram or contingency table. And lastly, you should be able to tell if event A and B are independent based on some calculations from conditional probabilities. So without further ado, let's do a demo. To start with, I'd like to point out the two ways of representing data in class we talked about. They are essentially the same, which is a contingency table and a tree diagram. They carry the same amount of information. So let me demonstrate how to start with a contingency table and end up with a tree diagram. So in this case, as you can see, I made up something completely random. We see 10 observations, both being male and being smoker, and for instance 40 of them both being female and they are non-smokers. What if we want to convert them into a tree diagram? We can ask the first question about gender, man and woman. So as you can see, we got 40 men in this population and 60 women in this population, and among these men we get 10 of them being smokers and 30 of them being non-smoker. And we have this similar question for woman group, and we got them 20-40, smoker and non-smoker. And you might wonder, sometimes you see a probability-based tree diagram as opposed to something like this. In this case, we only have counts or frequencies for each of the branch. So how to convert them into a probability-based tree diagram? We just have to do some math. In this case, 40% being man, so that's 0.4, 60% being woman, and that's 0.6. So in this branch, you want to use 10 over 40 because you are on a branch in which you only have men, so you only have 40 of them and use 40 as denominator. And similarly, you use 30 over 40 to calculate the proportion of non-smokers. So smoker, non-smoker. And of course, if you are willing to do some math, 10 over 40, which will give you 1 over 4, which is 0.25. And similarly, you can get 0.75 in the lower branch. And in this case, we are only looking at women, so that will give us 20 over 60 because we only got 60 women, and 40 over 60. And if you are willing to do some math, 20 over 60 will give you 0.33, and the second branch will be 0.67. So this is how to convert a frequency-based tree diagram into a probability-based tree diagram. Next up, how to get the conditional probabilities. Actually, we did this already. This 0.25 is the probability of, given you are a male, the probability of being a smoker. So we can carry on the same interpretation for every single one of them. 0.75 is the probability of being a non-smoker and being a male. And 0.33 is the probability of being a smoker, given that you are a female or woman. And 0.67 is the probability of being a non-smoker and you are a woman. So this is conditional probability. Next step, what if I want to calculate the probability of both being a man and a smoker? So in order to calculate this, I want you to recall the formula to calculate the conditional probabilities. Okay, this is scratch paper. This is how we do this. Or in other words, in order to calculate A and B, we can flip this formula into something like this. See, this is how to get the probability of A and B. So similarly, in this case, if you want to calculate the probability of both being a smoker and being a male, this is how to calculate this. This is a conditional probability multiply the probability of being a male in the sample. So we have got this already, do we? Given a man, what is the probability of a smoker? 0.25. And what is the probability of selecting a man from your sample? Remember, we got 40 of them over 100. So that's 0.25 multiplied by 0.4, and you got 0.1. So that is how to calculate the probability of both being a smoker and a man. In the tree diagram, I want to point out this. So if you have a tree diagram and you just multiply 0.4 by 0.25, this probability is the probability of being a man and a smoker. See, this is just what we've calculated, 0.25 multiplied by 0.4. In other words, if you are just multiplying probability along the tree line, you will get AND probability. So similarly, in this branch, if you multiply 0.4 by 0.75, what you will end up with is the probability of being a man and a non-smoker. So I'm going to do this again. If you use 0.6 multiplied by 0.33, you will get the probability of both being a woman and a smoker. And last, if you are multiplying along the last tree branch, that will give you the probability of both being a woman and a non-smoker. Okay, two things to bear in mind. First of all, this place, this place, this place, and this place, they are all conditional probabilities. If you are, on the other hand, multiplying along the tree, then you will end up with this AND probabilities. So that is how to use a tree diagram. Last stop, what if you want to find A and B and A given B with a contingency table? Let's find out. Again, just the same thing. But in this case, we want to use this contingency table to find out these two probabilities. The first one is, okay, both being a man and being a smoker. And the second probability is, given that maybe a woman and she is a smoker. So how to find that out? In order to find the first probability, we want to find all the individuals that qualify this criteria, both being a man and being a smoker. It is this cell. So we use 10 over everyone, right? So you get 10 over 100, and that is 0.1. In order to find the second one, you have to look at all the women you have. So we only focus on the woman group. How many we have them? We have 40. We want to look at the smokers, 20 of them. So that is 20 over 60, and that is 1 over 3, which is 0.33. The last thing I want to talk about is how can we tell if event A and B, they are independent with each other based on some calculation from conditional probability. Okay, this is how we can do this. We want to check if this is equal to this. If the equal sign holds, that means the fact that event B happens have nothing to do with event A. If that is true, then we can claim that A and B, they are independent. And following the similar logic, we can also check this. And this means the event A happening has nothing to do with B, which also infers the independence among A and B. The last thing that you can check is this. The A intersect B equals to probability of A and probability of B. If this one is checked, you can also claim that A and B are independent. These three equations, they are equivalent, and that means if one of them is checked, which means the second and the third will follow. You don't have to manually check all of them. So let's see how to use this in our example. So let's denote in our case maybe event A as being male and event B as being a smoker. We want to figure out if being a smoker and being a male are independent or not. So what we've already got is this probability. Given a male, what's the probability of that he is a smoker? If you can remember from the notes, that probability is 0.25. The only thing that we don't know is the probability of generally a smoker in the population. So in order to find that, we can go back to our contingency table and then find out how many smokers we have totally in this case. Well, we got 10 in men and 20 in women, and that is 30. So the probability of finding a smoker in this sample is 30 over 100, which is 0.3. These two probabilities, they are not equal to each other, and if that is the case, we can say S and M, they are not independent, which means the gender has something to do with the smoke status. Well, this conclusion is not decisive because, this data is completely made up, but this in general is how to find out if event A and event B are independent or not.